Hello, everybody. All right, so this is the last lesson of Unit 2. This is Grade 11 University Level Physics, Unit 2, Lesson 4, Gravity. So we can finally talk about gravity from a general, kind of a Newtonian general standpoint of gravity. Okay? So we're going to have to come up with an equation to represent gravity for any object. Okay? So um, we know that gravity as a force, it attracts objects towards the center of the Earth, right? That's what we feel all the time, right? The Earth is 10 to the 24 kilograms. We're like 10 to the 2 kilograms. So it's much, much heavier than we are. But because it's so heavy, it attracts us. Gravity is really actually quite weak, but let's not go there. Newton figured there must be a more general force because he was studying the planets. He was watching, he was looking at data of planets as they go around the sun, and he was trying to figure out a way to express all this. And before that, we're talking about this is in the 1600s, right? So there was angels pushing on the planets to make them go around. But he wanted to come up with a more mathematical way of doing this. Um, you could argue that the angels are just not pushing the planets, are pushing in, but whatever. It's centripetal force. Talk about that in grade 12. Anyways, so Newton figures there must be a more general force between the objects. After studying the orbits of the planets, so he went and got a whole bunch of data from various people, he showed that the orbits of the planets are determined by some proportionalities. The first proportionality says that the more mass there is, the more force there is. The heavier the planet is, the more force there is. The heavier the object is, which makes sense. More inertia, more force, more gravity. Okay? And the more brilliant proportionality statement was stating that the force follows what we call an inverse square relationship. And what does that mean? Okay, inverse, so that's 1 over, square. So it's proportional to, as we see here, 1 over r squared. And why does it do this? And we got to think about surface area here, for example. Let's imagine, so this force that's happening, let's say there's some object here in the center that's producing a force. We're going to assume that, and it makes sense, we're going to assume that this force is spherically symmetric. There's no direction that's chosen. It's everywhere. It's heading outwards symmetrically, right? And what that means is that it's going to basically produce this sort of sphere of influence. Okay? And let's say this sphere is r meters in radius. So the surface area of the sphere will be 4 pi r squared. So let's say there's some stuff. There's a certain amount of stuff coming out from the source. And at r, it's me going through some little area here, which will be the intensity, the amount of how strong it is at r is going to be equal to how much there is divided by 4 pi r squared. Okay. Now, if I double the distance, I'm going to double r, which will quadruple. See, so I have one area. Now I have 4 areas. When I double the distance, I quadruple the area. I stretch it by a factor of 4, which reduces the intensity by a factor of 4. Think about like a balloon. Okay? Think about the amount of material in a balloon. When you have it blown up just a very small amount, the stuff is still quite thick. But the bigger you blow up the balloon, the thinner the material gets. So in the same way, the intensity reduces. There's a very famous analogy of bread. And let's say you have a certain amount of margarine, butter that you want to put on the bread. Okay, so I have a certain amount of butter, and I spread that over one piece of toast. That's at R. If I now expand to a radius of 2r, I'm going to end up with 4 pieces of toast. So I'm going to reduce the amount of butter on each piece by a factor of 4. Right? I have to take my amount of my allotted amount of margarine and divide it into 4 pieces and spread it out to each one. Now, if I take 9 right? If I go to a distance of 3r, it's going to be 3 times 3, which is 9. So I'm going to have 9 pieces of toast, and I'm going to have to spread that same amount over that 9-tupled area. Okay, so as we increase the radius, we double the radius, we decrease the intensity by a factor of 4. It's inversely proportional to the distance squared. And now this doesn't only work for gravity. This works for electric charges, magnetic forces, magnetic forces. Any spherically symmetrical force obeys an inverse square law. It's really cool. Okay, just think about bread. Toasting bread. Okay? Sorry, buttering bread. So we put it all together and we come up with this proportionality statement. The force of gravity is proportional to the two masses and inversely proportional to the square of the distance between them. Be careful here. When you say r, you think about r as a radius, but really we're saying that r is the distance between them. But still, this isn't very satisfying. There's no equal sign here. There has to be some sort of constant that puts this together, that makes this proportional. So we need to make them equal with a proportionality constant. We're going to give that the letter capital G. And it took about another 200 years for another English physicist. So Newton did this in the 1600s, early 1700s. But Cavendish did a bunch of work. Cavendish is a very strange person, but we won't talk about that here. He was able to come up with an experiment to very carefully calculate the influence on. He basically put a bunch of some steel balls on a rod with a little string holding it, and then he brought other steel balls towards them and saw as it twisted this arrangement, he was able to carefully come up with this number of G. Okay? And we put it all together and we come up with the Newtonian universal gravity formula. GMM over r squared. Okay, so the force of gravity measured in newtons is equal to the mass of the one object times the mass of the other object divided by the square of the distance between them, and then multiply that by 6.67 times 10 to the negative 11. Okay, and notice the units on G: Newton meters squared per kilogram squared. And why is that? Well, think about this. This is going to be in kilograms here. This is going to be in kilograms. This is going to be in meters, so it's going to be meters squared. So we need it in newtons. So we're going to have newtons, because we want newtons, but we want to cancel out the kilograms. So we're going to put kilograms squared below, and we want to cancel out the meters, so we'll put that on top. So the units of G are going to be Newton meters squared per kilogram squared, because these kilograms squared will cancel these 2 kilograms, and meter squared will cancel this meter squared, and we're left with just newtons. Okay, that's how proportionality constants work. They allow us to make the units work out. All right? So let's do oh, wait a second. Uh-oh. Didn't we say that the force of gravity is just mass times G, where G is 9.81 meters a second? Didn't we have that expression? How can we have two? Well, let's think about this for a second. Let's write it out. Okay, this is GMM over r squared. Now, if we're on Earth, the two masses are my mass, m, and the mass of Earth. And the r, the distance, is the distance between myself and the center of the Earth. So, if I replace m with me, let's say mass of the Earth, and r with re, the radius of the Earth, I have this expression here, this constant, GME over r squared. Mass of the Earth doesn't change much. Okay, who cares? Radius of the Earth isn't going to change much. And G is a constant. So this is the constant term. My mass can change. So I'm almost there. I have that the mass is proportional to the gravity. But what happens if I plug in the numbers for these things? Okay, so G is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Mass of the Earth is 5.98 times 10 to the 24 kilograms. If ever you're stuck with these numbers, they're on our reference sheet. Okay, radius of the Earth 6.38 times 10 to the 6 meters, all squared. What happens when I plug it in a calculator? I end up with 9.8 newtons per kilogram, which is the same as G. So basically, it's the exact same thing. G, our constant, our lab frame, our Earth, surface of the Earth acceleration is just a special case of our universal gravity formula. On the surface of the Earth, this G, this gravity, would change. If I go to the moon, all I would have to do to calculate that is substitute in the mass of the moon and the radius of the moon, and I would end up with about 1.6 newtons per kilogram. Okay? So really, it's the exact same formula. Okay? So it's the same thing. It's a F equals mg is a special case of our universal gravity formula. All right? So we can try some examples here. Let's say we have a car and a truck, a 3,000 kilogram car and a 10,000 kilogram truck. They're 2 meters apart. All we have to do is take our formula, plug in our numbers, being careful with our calculator with our 10 to the whatevers, and we end up with 1.0 times 10 to the 3 newtons, 10 to the negative 3, so that's a millinewton. So a car and a truck next to each other have an attractive force of a millinewton, whatever that means. Okay, so even though they're attracted to the Earth, and that's going to be the dominant force, right? So that, for example, that truck will be 10 to the 4, that'd be 10 to the 5 newtons of force pushing down, just on that truck. Okay, so the dominant force will be that. But if we took those two objects and we stuck them in space and put them in a perfectly flat space with no other masses around, if I stuck them there and I let them float, they would be attracted to each other with 1 millinewton of force, and they would slowly come together. That's why everything slowly comes together. You have you know, a ball of gas, a ball of hydrogen floating out in space. Slowly all those hydrogen molecules will attract to each other, and eventually it'll form a sun because the gravity of all those things compresses itself down. What about the force of gravity between the Earth and the sun? Same thing. Take our formula, plug in our numbers. They're much larger now. The mass of the sun is 10 to the 30 kilograms. 2 times 10 to the 30. That's 2 and then 30 zeros after it. Big number. But the distance is also quite large. But it ends up working out to 3.52 times 10 to the 22 newtons. It's a huge force. They're huge masses as well. So it's not that... It's the reason why the Earth is going around the sun. This is the force that's keeping the Earth in orbit. The Earth is falling, right? That's what an orbit is. There's the sun, and here's the Earth, okay? The Earth is falling because it's being attracted, but it falls in the perfect way. The definition of orbit is a perfect trajectory so that it falls forever and forever misses. If it was off a little bit, if it was going faster, it would slowly go and then it would just escape. And if it was off a little bit this way, it would slowly crash into the sun. But it's in this perfect orbit so that it always ends up going around and around and around in a circle. That's the definition of an orbit. And the reason that it's in orbit is because there's a force pulling inwards that we just calculated. 3.5 times 10 to the 22 newtons. All right? So, oh, my scribbles are underneath that. Let's erase my scribbles now. Sorry about that. So the Earth and the Sun are attracted to each other with a force of 3.52 times 10 to the 22 newtons. Wow. All right, so here's some problems. You can work on these. 3 to 7, please. The answers are all up on the Weebly as well. But before I let you go, you can stop here if you'd like. But I can't talk about gravity without talking about a sort of modern view of gravity. This is what we've done now is the Newtonian gravity view, and it's correct. It's totally correct, but it's a special case of a deeper theory. Gravity, the gravity that we see is this thing that we've just done works perfectly, but it doesn't tell us why. And the reason why is figured out a little bit later. Well, most of the reason why we still have lots of questions. But in the after Einstein's work on relativity in the, between 1906 and 1911. Okay. And it's still being worked on, but our modern view of gravity is a little bit more complicated. And it has to do with what we call the curvature of space-time. Okay, again, if that just scared you, stop the video, do your problems, who cares? If you want to learn a bit more, just keep going, okay? This little GIF here shows us how an orbit works from the relativistic point of view. The sun doesn't actually create a force of attraction. What it does is it changes the shape of space-time. What the heck is space-time? Okay, that's the four-dimensional view of everything. There's three x, y, z as our three space directions, and then time as our fourth dimension. And time and space are sort of stuck together. Once you start going fast, closer and closer to the speed of light, space and time get sort of confused. And I mean that truly by the word confused. They kind of get stuck together. Okay. And it gets kind of strange. Very strange. Okay. So we can simplify that four-dimensional view into a simple two-dimensional grid. And we can show that a mass, the sun here, warps that two-dimensional grid. Think of it like a think of it like a trampoline. If you stand on a trampoline and you let some marbles go, those marbles will appear to be attracted towards you. Right? If you don't know, if you're looking from a top view, if you have a drone above you looking straight down and it doesn't see the curvature, it doesn't see how the space has been, that flat surface of the thing hasn't been bent down, it'll just appear like those marbles are coming towards you. So here we can see the Earth. What it's doing is it's following a curve, a circular curve around the sun. It's falling down that curve constantly. It's falling again in that perfect, call it a geodesic, a perfect path that keeps it contained, keeps it going around and around and around forever. Maybe you've seen this when you go to a mall and they have that big sort of like yellow funnel thing and you put a penny in and it whizzles around. It eventually goes down because of friction, but there's very little friction out in space. So the Earth, once it's got that speed, will continue along that geodesic in our four-dimensional space-time. And again, this is a two-dimensional view. We've warped in the third dimension. Very difficult to grasp in our heads. Our brains cannot contemplate four dimensions. We can see it maybe a little bit better in three dimensions. Not a little bit better. This is even more confusing. Whatever. What am I saying? But in three dimensions, it sort of warps the meter stick of the world, of our local space-time. You say, objects fall down towards the Earth through gravity, but the gravity is only there because the mass of the Earth has bent space-time. Wow, that's a lot. Okay, and space-time can do very strange things. It can spin, right? We are able to actually we are actually able to prove that it does spin. There was a probe was sent up. The world's smoothest object was a big 2-meter ball of iridium or something. I forget what it was. This ball, and it was smoothed down to like perfect smoothness, so it would have no imperfections and no diagonal terms, and only diagonal terms in the tensor, whatever. It was a perfect. There was no weird effects to it. So when it would spin perfectly. And they were able to use that probe as it was going around the Earth to see what we call the frame dragging. That not only in this picture, not only does the frame, this grid, does it not only just come down, but it actually gets twisted a little bit by the twisting of the Earth as it spins. Okay. This is crazy stuff. And another thing that it can do is it can actually produce waves. What you're seeing behind me, where I'm at right now, where I've been sitting this whole time, is in the LIGO detector, which is a gravity wave observatory. There's actually 3 of them around the Earth, and they're actually being used currently to determine, collisions of black holes. When black holes collapse on each other, black holes, they start spinning around each other and then actually collapse onto each other. They release a stupendous amount of energy. And what that changing in mass and energy does is it actually creates a wave, a ripple in space-time. And what that does is this 4-meter long laser beam actually changes its length because the actual frame, the actual grid of the local space-time changes. So we can actually see there's actually two lasers, one going this way and one going this way, and they're at right angles to each other. And we're able to measure the changes in the 4 kilometers. There's only, micron difference, or sorry, even smaller than that, angstrom difference. No, it wouldn't be. It would be like 10 to the 3. It would be like 10 to the 10 to the negative 10 difference in the length of these lasers. But they're able to measure that by seeing how the lasers interfere with each other. We can talk about that. You'll talk about interferometers in grade 12, sorry. Okay, so this detector here actually sees gravity waves by seeing how the frame of our local space-time changes under huge gravitational forces, under these massive gravity waves that happen when black holes collapse on each other. Okay, and if you're on Twitter, look up LIGO. They'll always show you any sort of results they see, any sort of time they see a black holes collapse on each other. They'll show you the data that they actually get. Okay, so and if you really want to go, if you haven't stopped the video yet, you're probably gonna stop the video here, because what we're gonna look at is some math. Look at that. This is Einstein's equation. Oh God, and it looks awful because it is. These are covariant tensors. These are Rishi tensors and that sort of stuff. Yikes! But really, don't worry about the math. All this is saying, okay, the fundamental idea is this is geometry over here. If I can spell. So this is a geometrical term. This is the curvature of space. And this is just a constant. Notice G again, our big capital G. C, speed of light. And this thing here, this is called the stress tensor, which basically is physics. It allows us to do dynamics. So the physics is an implication of geometry. How things behave are caused by the change in the local space-time curvature. So geometry leads to physics, which is mind-boggling. This thing here, this is Hubble's constant, and we're still looking at that. We're still trying to figure out that piece. If it is less than 1, then the universe will collapse on itself. If it's exactly 1, the universe is in a steady state, and if it's greater than 1, the universe will expand forever. Big Bang caused the universe to expand. Long term, if that number is greater than 1, it'll expand forever. We think it's just a little bit greater than 1, according to latest results. But again, all this stuff is brand new. We're still working on all this stuff. That's the great thing about physics is it never ends. The more answers we get, the more questions. Okay? All right, so sorry about that little rant on general relativity and modern gravity and all this sort of stuff. Just keep in mind, we don't really know. I'm going to add a link to a video with Brian Greene. He's a string physicist, basically a mathematician who looks at theoretical models of physics, and shows some of our latest understanding of the actual fabric of the universe. What is space-time? What is space? Is space just empty? Is there some meter stick? Okay, anyways. All right, so best of luck and stay safe, guys.